Okay. Okay, when did the last thing stop? Did it stop at the right time or did it stop late? Because you should have a 10-minute break in between. Have you had a 10-minute break? Yes or no? I mean, should we start now or should we start after 5 minutes? No
Sir,
response.
you're up for it. We can start now.
Okay, we start now. Okay. So, as I said, I'm still waiting for responses for that Casorati-Weierstrass theorem. One person has responded and he has given the right answer. But that really does not count because I believe that person was in one of the classes that I have taught some time ago. And I believe that I think I must have made a fuss about it in that class. I normally make a fuss about it in every class that I'm in because this is something that people don't realize that there are problems. So anyway, just think about it. And the other thing is, yeah. So are there any questions so far of what we did up to now? Anything you want to ask? Because I haven't got any emails from any of you, very few of you. And I'm not really sure whether my notes are readable or not readable. I hope they're readable, but I can never be sure how much is getting through. No? No comments or no questions so far? No. Yeah, something? Deepak, you wanted to say? No, he's off. Off and on. People go off and on. Okay, let's continue. So what should I do? I should minimize this. And then, yeah, so this is what we were doing last time. The first thing was this mean value theorem for holomorphic functions. And for those functions which are the real part of holomorphic functions, you also get the mean value theorem. And then, of course, there was this question that if you have a function, a real valued function which satisfies a mean value property, can you conclude that it is a real part of a holomorphic function, which I had left hanging? Okay. And then I was beginning to talk about homotopic paths, which have the same initial and end points. Okay. So we had said that if you have a function is holomorphic in that region, in a disk, okay, and f is holomorphic on the disk, and you have two paths in the disk which have the same initial and end points, then integral over one of the paths of fz dz is equal to the integral of the other of the paths of fz dz, because when you take gamma 1, gamma 2 bar, that means you first go along gamma 1 and then go along the inverse of gamma 2. That means I'm going along gamma 2 in the opposite direction. Then it's a closed path and therefore the integral is 0, and therefore the integral over gamma 1 is equal to the integral over gamma 2. There's something that's going on here which I don't think I have said it very much. But the point is that if gamma is a path from z0 to z1, gamma of t lying in 0, 1, and then look at gamma tilde of t, which is gamma of 1 minus t, then gamma tilde is a path from z1 to z0, okay, and it traces out the same curve in the opposite direction, and integral over gamma 1 is equal to minus the integral over gamma 2, okay. This is something which I don't think I've written down, but you should try to understand that if I go integral f over a path is minus integral of f over the reverse path, okay? And this is something that you should be able to sort of understand intuitively at least, and then prove it. If you have a constant path, yeah, someone wants to say something. What?
Why I thought it's,
Yeah.
which is you go over the path and then it's a loop. So the integral is 0 over it and you break it off at.
But then you must say that integral over that reverse path is minus the integral of the first path. Okay. That is what you have to understand. If you go in the path in the reverse direction, then the integral of fz dz over the reverse path is minus the integral of fz dz over the original path.
Yes.
Okay.
I know, that's what I was saying, that if this is gamma, let's just say gamma 1 and gamma 1 minus gamma 1.
Gamma 1 tilde, it's denoted usually by gamma 1 tilde. Okay.
And the integral over gamma 1 tilde after gamma 1, this is 0. So, but you can also split up this.
Why? Okay, so there again you're using something. You're using gamma 1 multiplied by gamma 1 tilde is homotopic to the constant path. Okay. And integral over the constant path is 0. Yes. So, you are using that in gamma 1 multiplied by gamma 1 tilde. This path
is homotopic to the constant. Yes, I am.
Is homotopic to the constant path. Okay. And therefore the integral is equal to 0. So there's something that you're using there. Okay, if you want to say it in that way. But you can actually write down what those integrals are and see that the integral of the second one is minus the integral of the first one from the definition of what is the integral. Okay. I mean, what we are saying is that integral of f from 0 to 1, integral of ft dt from 0 to 1 is equal to minus the integral of ft dt from 1 to 0. Okay, it's that kind of thing that's going on. So it has nothing to do with homotopy actually. You understand what I'm saying? That integral of ft dt going from 0 to 1, lower limit is 0, upper limit is 1. Integral from lower limit 0 to upper limit 1 of ft dt is equal to minus the integral from 1 to 0 of ft dt. Okay, so that is what is actually needed there. You don't need any homotopy business, but the way you were talking about it, you did need the homotopy business. Okay, so we'll come to that in a little while. Okay, so the point is that if you have a constant curve, the integral is 0. And what here, the curves were contained in a single disk and f was holomorphic in the disk. But suppose the curves are longer curves and the curves are not completely contained in one disk, but they're contained in the union of two disks. And even then, you see, I can't use the fact that it is contained in a disk and therefore the integrals are the same because the curves are not contained in one disk. But if the curves are contained in two disks, union of two balls, then I can break it up in the middle and I'll get that the integral over one curve is the integral of the second curve by adding and subtracting that section that lies in the common intersection of D1 and D2. And therefore you can extend this to a finite number of disks, D1 to Dn. Okay. So you can have this picture with a finite number of disks. Have I drawn it? Yes, I've drawn this finite number of disks that cover gamma 1 and gamma 2. And by the same argument, you'll get this integral is that integral. Okay. So if gamma 1 and gamma 2 are two curves which can be covered by disks in this manner, integral of gamma 1 is equal to integral of gamma 2 is equal to z. Okay. And the question is that, how do you might not have that this is always true, that you can cover these gamma 1 and gamma 2 may be very far apart. And what do I mean by that? What is the what is the example that you have at the back of your mind? The example you have at the back of your mind, I should have drawn this here, okay, which I have never drawn it. No, I have not. So here, please note that the example, when I'm saying this, what does this happen? Why is there a problem here? Is that you take omega to be the complex plane minus the origin. Okay. So your omega is complex plane minus the origin. Gamma 1 is the path that goes from 1 to -1. It's a semicircle in the upper half plane. And gamma 2 is a semicircle in the lower half plane, which goes from 1 to -1. Semicircle of radius 1. Okay. So the picture I have is that I have this boundary, the upper semicircle and the lower semicircle in the unit disk. Okay. Sorry, in C, I'm thinking of the upper semicircle and the lower semicircle. Both are paths from +1 to -1. Okay. And omega is C minus 0. Okay. And then can I cover these paths by a family of disks? Okay. In omega, such that that previous thing happens. This is one example you should keep in mind. And the other example you should keep in mind is that, again, gamma 1 is the semicircle, omega is C minus 0. Gamma 1 is a semicircle in the upper half plane from 1 to -1. And gamma 2 is a loop that goes way out, say to crosses the imaginary axis at say z equal to 500i and then comes back down. So it's an oval thing like that. Okay. Now the question is, can you cover it by disks? Actually, you can, but anyway, that is a separate issue. So there's a problem here that when can I do this? Okay. So omega is a domain. You have 2 points in omega. Gamma 1, gamma 2 are from 0, 1 to omega are paths which have the same initial and end points. Okay. We say that gamma and gamma 2 are fixed endpoint path homotopic in omega. Okay. So they must have fixed endpoints, and they are, actually I should say, endpoint path homotopic. Doesn't really matter. Okay. And it must be in omega. So this in omega is important. This in omega here is important. If there exists a continuous function h from 0, 1 cross 0, 1 to omega, such that when you put the second component equal to 0, you get gamma 1 of t. When you put the second component equal to 1, you get gamma 2 of t. And when you keep the first component 0, that means these paths always start at z0 and the paths always end t equal to 1 at z1. Okay, so that means that if you look at gamma s of t, this is the path at the level s. This is a path between z0 and z1 for all s. Okay, so for each s horizontal line, okay, s equal to constant is a horizontal line. S is the second component. S equal to constant. That means the y coordinate is constant. It's a horizontal line. It's a function of t. That gives you some path. And we are saying that this path for each horizontal line s equal to constant, okay, that function of t is a path between gamma naught and gamma 1. So this is my definition of gamma 1 and gamma 2 are fixed endpoint path homotopic in omega. The in omega is that this image is in omega. Okay. And the way that one talks about it is we say that gamma 1 can be continuously deformed into the curve gamma 2, keeping the endpoints fixed with the endpoint homotopy h. Okay. So I should have written that whole thing out, that if gamma 1 and gamma 1 can be continuously deformed in omega to the curve gamma 2 by the homotopy h. So I should have written continuously deformed in omega. Okay. It is important to say that it is in omega. Okay. And the theorem is that if gamma 1 and gamma 2 are homotopic, then integral of gamma 1. So f, what is f? F is holomorphic. So here I'm taking a holomorphic function f on omega. I'm taking two paths in omega which are homotopic and have the same initial and end points. Then my statement is that integral of f over gamma 1 is equal to integral of fz dz over the curve gamma 2. Remember, the endpoints are the same. So we are saying gamma 1 and gamma 2 are homotopic. So there's a homotopy between this and this. Okay. So for each TS, h of TS is in omega, which is open. So h is continuous. So at TS, you can find a little ball such that h of TS is contained in a disk with center HTS, which is contained in omega. This is the definition of continuity. I'm only using continuity of h. Okay. So given there exists a disk around this such that the inverse image of that disk under h contains this ball. Okay. I'm being slightly vague here, but doesn't really help being much more precise. So these ball center TS radius delta is an open cover of the compact metric space 01 cross 01. And this is something where you have seen this earlier, but you probably have forgotten about it. Okay. You have a metric space and you have a compact set in that metric space, and you have an open cover of that compact set. Then I can find a Lebesgue number for this open cover. Okay. What is a Lebesgue number?
So you take balls of radius. The Lebesgue number you're denoting by eta. Take balls of radius eta. They're going to be within one of the sets which is forming the.
So there exists an eta greater than 0 such that any ball of radius eta, okay, or any set, open set, which has diameter less than eta, is contained in a single ball of that open cover. So the statement is that if you have an open cover of a compact set in a metric space, so let U alpha be an open cover of a metric let U alpha be an open cover of the compact set K in a metric space. Okay, then there exists a delta greater than 0 such that any ball of radius delta is contained in one of those sets in that open cover. Okay, so you can cover it, you can find these balls of some positive radius such that any ball is contained in one of the open sets. Yeah, so again, if those of you who are not very familiar with it, I hope you will go back and revise. All of you have seen this earlier, and I hope you will revise what the meaning of this Lebesgue number is. It comes up every now and then. This notion of a Lebesgue number comes up. When you have a compact set, so Lebesgue number comes up when you have a compact set in a metric space and you have an open cover of that compact set, and then you can find this delta such that any ball of radius delta, okay, in that compact set is contained in one of the balls in the open cover. Again, this is a good thing to write down your epsilon delta definition. Okay. And I hope you write down the epsilon delta definition correctly. So choose 1 over n less than eta. Actually, I don't think 1 over n less than eta. I should choose n so that 2 over n is, or 3 over n is less than eta, or 1 over n is less than eta by 10. Doesn't really matter. Okay. Then you break up 01 cross 01 into these subintervals, k by n to k plus 1 by n. So just instead of 1 by n is less than eta, you put 10 by n is less than eta. 10 by n definitely works. It doesn't really matter. Okay. I have to be slightly careful there, which I have not been careful there, but anyway. So choose n so that 10 by n is less than eta. Eta is the Lebesgue number. Break up the x-axis, break up 01 cross 01 into these small squares, each of which have sides which are parallel to the axis of length 1 by n. Okay, so the diameter of each of these is less than eta by 10, and therefore the image under H of these is going to be contained in a single disk in omega. Okay. Now I look at these two horizontal lines, gamma k by n and gamma k plus 1 by n. Okay, gamma k by n of t is gamma t comma k by n, and gamma k plus 1 by n by t is gamma t comma k plus 1 by n. And each of those squares are contained in a single disk. Okay, so I have covered gamma k by n and gamma k plus 1 by n by disks, okay, such that those sections, each of those finitely many sections are contained in a single disk, okay, and gamma k by n and gamma k plus 1 by n have the same initial and end points, namely z0 and z1, gamma 0 and gamma 1, okay, whatever, gamma 1 0 and gamma 1 1. And therefore, by the statement I made earlier, the integral over the curve gamma k by n is equal to the integral over the curve fz dz over the curve gamma k plus 1 by n. What is gamma k by n? Have I told you what gamma k by n is? I think I have. Let me just check. Gamma s of t is h of t comma s. So gamma k plus 1 k by n is h of t comma k by n. This is some curve from between z0 and z1. So I've told you what gamma k by n is. Yeah, so I'm not having a gap there. So the integral over each of these is the integral over the next one. Yes, and therefore finally you get the integral of the horizontal first. Gamma 0 is the same as the integral over gamma 1 by n, which is equal to gamma 2 by n, integral over gamma 2 by n, which is integral gamma 3 by n, which is the integral gamma n by n, which is gamma 1. Okay, so there is some induction business here. Now this kind of idea actually is important. Okay, you will see this idea in at least a couple of different contexts, and this is why you can use homotopies to go from one to the other. So what does this say? This says that if you have two paths in a domain, okay, which are homotopic by a homotopy in that domain, I'm again and again emphasizing the fact that the homotopy between these two curves, gamma 1 and gamma 2, the homotopy must be having its image also contained in omega. And this is sort of a delicate point which people tend to overlook, that when you're talking about these homotopies, the domain is important. Sorry, not the domain. What am I talking about? The codomain is important, or domain H, going from H is from 0 1 cross 0 1 to omega. So it is the domain that is important. Okay, if the domain changes, then you can't talk about this homotopy. Or if the value of the homotopy goes outside that domain, in particular, if the domain is C minus 0, you must be sure that the value of H, the homotopy, never hits 0. Because if the value of the homotopy hits 0, you can't do this business, because H is a homotopy in omega you must have. So this is something to be kept in mind, that it must be a domain. The image of the homotopy must be in omega. H must take values in omega. Okay. So moral of the story is, if you have this domain and you have two paths in them, and you have a holomorphic function on the domain, and these two paths are path homotopic, then the integral of fz dz over the first path is integral of fz dz over the second path. Okay. Now a domain is simply connected if any two paths in omega with the same initial and end points are path homotopic. Okay. So every path is homotopic to every other path in omega. Okay, the homotopy must be in omega. And then, of course, you must ask yourself questions of, give me an example of domains omega in which any two paths are simply, give me an example of a simply connected domain and an example of a domain that is not simply connected. So the example of the simply connected domain is a simply connected domain is
an open disk.
So why do you want to take an open disk? It's C itself. Okay, you take the whole complex plane, it is simply connected, because if you take any two paths in that, then the straight line segment joining these two paths is going to give you a homotopy. Okay, and this is the whole plane. The straight line segment will also be in the whole plane, so this will be a homotopy between the two paths gamma 1 and gamma 2. What am I talking about? I'm talking about h of t comma s is s times gamma t plus 1 minus s times gamma 2t. Okay, and therefore this is true on any convex set. So if you have a domain that is convex, then a convex domain, what is the meaning of convex domain? Convex domain says that any 2 points in that domain, you take any 2 points in that domain, then the straight line segment joining those 2 points is also in the domain. Okay, so every convex domain is simply connected. Number one. Okay, number two is what? What is a domain that is not simply connected? And the answer is obvious. The answer is going to be
S1.
S1 is a bit too complicated. Don't talk about S1. Okay, yeah, I mean, the easier thing to think about is take C minus 0. Remove 0 from the complex plane. Okay, S1 is the right answer. Okay, but I want a domain. That means I want an open set. Okay, and S1 is not an open set. Okay, so yeah, I mean, the idea is correct, but a domain has to be an open set. Okay, so you take C minus 0, and my claim is that C minus 0 is not simply connected. Why?
So you can take the boundary of the whole, then the loop around I
have just proved it to you. Why is C minus 0 not simply connected? So what have we done? We have said that if you have a domain and you have a holomorphic function in that domain, then the integral of your holomorphic function f, which is holomorphic in the domain omega, then integral of fz dz is independent of the path integral of fz dz, okay, for any two paths which have the same initial and end points, the integrals must be the same. Yes, that is what we have just done. Correct? So if you take C minus 0, what is the obvious holomorphic function you should think of?
1 by z.
1 by z. Okay. So you take fz equal to 1 by z. Fz equal to 1 by z is holomorphic in the domain C minus omega. Then I want two curves. What are the two curves over which you will integrate fz dz? The first curve is going to be
Circle at 0 of radius 1.
Circle. Okay, you can take circle at 0 of radius 1. And the second one is going to be?
Circle of radius 1 at 500.
No, these two integrals are the same.
Any circle which does not contain the point 0.
No, that will also not give you the right. What do I want? I want two curves, gamma 1 and gamma 2, which have the same initial and end points. Okay, but the integral over one and the integral over the second are different. What are the curves gamma 1 and gamma 2 that you will take? The function is fz equal to 1 by z. It is holomorphic and c minus 0. So the curve should be, the first curve you tell me is the circle around the origin of radius 1. Correct. What is the second curve you will choose? What is the initial and end point of that curve?
Circle which touches at point 1.
No. Like, go back a bit. So the first curve gamma 1 is the curve which is the circle around 0 of radius 1. This is a curve gamma 1 in c minus 0. What is the initial point of this curve? It doesn't matter. So which initial point will you say this curve is? The curve has initial point.
So 1, 0.
And end point?
Itself 1, 0.
So the initial point is 1, 0 and the end point is 1, 0. So now I have a curve gamma 1, which is a curve in c minus 0 with initial point 1, 0 and end point 1, 0. What is integral fz dz?
2 pi I.
2 pi I. Now this is for gamma 1. What curve gamma 2 will you choose?
So circle at 2 of radius 1.
No, you see, the point is that circle at 2 of radius 1 with initial point
1, 0.
and end point.
1, 0.
Actually, what you're saying is correct. Okay, but I didn't want this answer. The answer I wanted was that one is a circle around 0 of radius 1 of starting at 1, 0 and end, 0. That is gamma 1. And what will you choose gamma 2 to be? Which is the simplest choice of gamma 2?
The same circle with opposite direction.
No. Then your initial point, it's sort of, will that work? Actually, that will also work. The initial point is the same and final point is the same. So what you're saying will also work, but I want something easier. What is the easier thing you will take? So do you understand? I can take gamma 2 to be the constant curve at 1, 0. Single point. Yes. And what is the integral over gamma 2? It is gamma 2 is the constant curve, single point at 1, 0.
The integral is 0 then.
So the integral over gamma 2 is 0. Okay. And therefore, these two curves cannot be path homotopic. Okay. So what I'm saying is that the circle which goes around it once cannot be path homotopic to the circle which remains at 0. I'm not circle, to the path that remains at 0. Okay. So this is the simplest example of a domain that is not simply connected. Okay. And this is the way you always do something. Okay. To show that something is simply connected, you have to take any two paths and show that these two paths are path homotopic. To show something is not simply connected, you just have to have one example of a function which is analytic and an example of two curves, gamma 1 and gamma 2, so that integral of gamma 1 is not equal to integral of gamma 2. And this always happens, okay? To show something is not true is usually more difficult to show than to show something is true. Because to show something is not true, you only have to give an example where that thing is not true. Okay. Anyway, this is sort of philosophy going back to it. What do I want to do? I want to go here, I think. So a domain is simply connected if any two paths with the same initial and endpoints are path homotopy. In a simply connected domain, if f is any holomorphic function and gamma 1 and gamma 2 are two curves in gamma with the same initial and endpoints, the integrals of gamma 1 and integral of gamma 2 is equal to 0, and therefore if gamma is closed, then gamma 1 is homotopic to the constant path at the initial point, and integral of the gamma of the constant path at the initial point is 0, and therefore if something is simply connected and gamma is closed, integral of fz dz is equal to 0. This is what. In a simply connected domain, any holomorphic function has a primitive. Why? This is a standard thing. Okay. Suppose you have simply connected, then the integrals are independent of the path, and I'll define g of z to be the integral of fw dw over gamma, where gamma is any path in omega. Okay. Gamma is any path in omega from a fixed point z0 to z in omega. Okay. And oh, this is now I should get to the other page. Why is this well defined? This is well defined because if you have any other path, the integral is still the same. Then I have to show that g prime of z is equal to f of z. So how do I show that? So which one do I want? I think I want this. Don't have anything after that. Where is my page 59? So 59, I have not. Oh, this is page 59. Oh, okay. So g of z is equal to this integral, and then you have to check that g prime of z is equal to f of z. Why? Because if you take g prime, what is g of z plus h? I want to go from z to z plus h. I can take any path from z to z plus h. So I take that horizontal path, which goes like this, horizontally, and then goes vertically. And then we have already proved that g of z plus h minus g of z divided by h, limit when h tends to 0, is f. Okay. You remember we have done this, that if you just take this integral, what is g of z plus h? It is the integral from z0 to z plus h of any path. Which path will I choose? I will choose the particular path which goes along gamma to z. Then you go from z horizontally and then vertically to z plus h. Then g of z plus h minus g of z is just that integral over that horizontal part and vertical part, which is the same as the integral of that straight line segment, and the limit when h tends to 0 of the integral of the straight line segment is f of z. Do you recognize that we have done this before? Yeah? To show that g prime of z is equal to f of z is something that we have done before, when I was taking a particular kind of curve, and I can use that again here. Okay. So, therefore you have a primitive. So this particular integral, g of z is holomorphic and g prime of z is f of z. Okay. So this every holomorphic function has a primitive. There exists g prime of z is equal to f of z. I hope this is page 69, 59. This is page 59. So a function fz such that e to the fz is z, where z is not equal to 0, is called a branch of the logarithm. Z is equal to r e raised to I theta. Okay, then e to the log r plus I theta is log r plus e to the I theta r e raised to I theta, which is z. So if fz is equal to fr e raised to is log r plus I theta is a branch of the logarithm. Okay, and you want this to be such that this function, I would like it to be log r plus I theta. I want it to be, in fact, holomorphic. But if not holomorphic, I want it to be continuous. And then you realize that there is a problem if I have this. What happens if I have, obviously I can't define this for z equal to 0. But even if I remove 0, I have a problem around this positive x-axis. Okay. So there are difficulties, for example, at z equal to 1/2, because when you go from z equal to 1/2 from the top and z equal to 1/2 from the bottom, you have a problem. Okay. So when can I do this? So if so, the statement is that suppose omega is simply connected. In a simply connected domain, which does not include 0 and which has 1. 1 is not very important there. But you take a simply connected domain which excludes 0. Okay. There is a branch of log z on omega such that f is holomorphic. You see here, when I just did this business, I had even problems with continuity. Okay. Because I can't really define what that theta is. Okay. So I don't even know how to define a continuous function on that. But now I'm saying that if the domain is simply connected and does not include 0, I mean, this domain that I had here was c minus 0, and I had problems with that. Okay. For example, in this case also, if I omit the whole real line, then the domain is simply connected and doesn't contain 0. So I can define a branch of the log. Similarly, if I omit any ray which starts at 0, straight line which starts at 0, straight line, my straight line. So if I omit any straight line which starts at 0, half straight line, then I can define log. Okay, that's what I'm trying to say here. So let omega be simply connected, 0 not in omega, and 1 in omega. 1 doesn't really matter, as I said. Then there exists a branch of fz equal to log z on omega. What are the properties that log z should satisfy? F must be holomorphic. E to the fz is z. That's why I'm calling it log z. And if r is real, then f of r should be log r. Okay, and r is close to 1. So I want to show that this capital F exists. Okay. How do I do that? So, this is the kind of argument that you are going to see over and over again. I want to prove that F exists, but I don't know how to find the F, capital F. Okay. So I will say that suppose I assume what I'm trying to prove. Yes. Suppose I assume that this capital F exists. Be very clear in your mind that this is what I'm trying to prove. Okay. So I'm assuming what I'm trying to prove. Then e to the f of z, capital F of z is little f of z. Okay. E to the capital F of z is equal to z. If capital F exists and it's holomorphic, so I can take the derivatives of both sides. So e to the capital F of z prime is equal to z prime, which is equal to 1. That means e to the f of z into fz prime is equal to 1, but e to the f of z is z, and therefore f of z is 1 by f prime of z is 1 by z. Okay. So if f exists, then f prime of z is 1 by z. So I define g of z to be 1 by z. Z is an omega. 0 is not in omega. So g of z is holomorphic on omega. Omega is simply connected, and therefore integral of gz, which is integral of 1 over z dz over gamma, this is well defined for any path gamma in omega from 1 to z. Okay, now there's a slight problem here. There's a z here, there's a z here, there's a z here, there's a z here, and there's a z here. Okay, and these z's mean different things. So I'm just writing it out again. Omega is simply connected. Fz is equal to 1 over omega, 1 over w dw, integral over gamma. Gamma is a path connecting 1 to z. Okay, 1 over w is a analytic function on omega, and this is independent of the path gamma. Okay, and then as before, you will have that capital F prime of z. Okay, what do? I take any path from z to z, 1 to z, and then I want any path from 1 to z plus h. Which path do I choose? I choose this path. This is what I meant by taking the horizontal and the vertical thing. Okay, we have proved that capital F z plus h minus capital F of z is equal to integral from z to z plus h along that straight line segment, and the limit when h tends to 0, it is equal to 1 by z. Okay, so this we have seen so many times, and this is what I had just been talking about. So f is analytic on why have I written on z? I should have f is analytic on omega, and d by dz of z times e to the minus fz is equal to 0. Okay, and therefore this must be a constant, and therefore you evaluate that constant at this equal to, where do I have it? Z equal to 1, and when z equal to 1, this is 1, and therefore e to the fz is z. Okay, if r is real and r is real near 1, then f of r, I take the straight line segment joining 1 to r of 1 over z dz is 1 over x dx, 1 over r, which is log r. Okay. So this is the standard way of saying that the branch of log exists on a simply connected domain that does not include the origin. Okay, you will understand that 1 does not really matter here, but the domain must be simply connected. Okay, and you must be careful to understand that log of xy is log x plus log y if x and y are real, but if z1 and z2 are complex, I've just defined this log to be capital F of z is log of z, and you have to be careful that this may not be equal to log z1 plus log z2, the way that we have defined it. And you should come up with an example to tell me that log of z1, z2 is not equal to log of z1 plus log of z2 for some z1 and z2. So be careful with that. Okay. Now again, I should sort of make a bit of a fuss about this point. Okay, which point? There's a fuss that should be made at this stage. Okay. Let omega be simply connected, 1 in omega this blah blah blah. I want to show that there exists an fz which is log z which satisfies these properties. And what do? I say, suppose f exists. Then capital F exists, then capital F must satisfy some properties, and then I'm using those properties to find capital F. Now, do you understand that this actually looks like as if it is a circular argument? I want to prove something, and then I'm assuming it is true, and then I'm doing something. Okay? And I hope you understand that this actually involves a certain level of sophistication. And if you try to explain this to someone who does not have much of a mathematics background, you are going to get, that person is going to get very confused because you're assuming something that you have to prove. And do you realize you were having the same trouble a long time ago when you were in your first or second or third standards in primary school? Where were you having this problem? Where were you having this problem that you were assuming what you want to prove and then you were going ahead and doing it? In primary school, first or second standard, you were having the same, you should have been having the same problem. What am I talking about?
So grammar,
Pardon me?
while learning Hindi grammar or English grammar.
No, not English, mathematics. While learning mathematics in primary school, you had this problem. Where did you have this problem? You were assuming what you wanted to prove. And I hope you were very confused at that time. I was, at least, I think. Where was it? No? Remember, there's a place in primary school when you said that how many apples should I add to 5 apples to get 8 apples? How did you do this problem? Do you remember? How many apples should I add to 5 apples to get 8 apples or bananas, whatever it is? How did you solve this problem in second standard? Or how did your teacher solve this problem in second standard? No?
Sir, I don't remember. How teachers have taught us that problem, I can't recall.
So let me tell you how your teachers did this. Your teachers did this by saying, how many apples should you add to 5 apples to get 8 apples? Your teacher said, let X be the number of apples you have to add to 8 apples to get to 5 apples to get 8 apples. Yes? So your teacher was assuming the answer X. Yes? And then your teacher did something, and then he came up with 3 apples. When I say she came up with, what a gender biased statement I'm making. Do you understand what I'm saying? How many apples do you add to 5 apples to get 8 apples? Your teacher said, let X be the number of apples that you add to 5 apples to get 8 apples. And I hope you were very confused because you don't know what X is. What is X? Yes? But your teacher was assuming the answer was X. And then going on and doing something. Is what I'm saying making sense? There's something very confusing about that. Yes or no?
Yes, sir.
I don't know if you have been in my classes earlier. I have said this earlier. Okay.
Yes, sir.
I sort of make a point of this to say this, that, you know, there are certain things that are going on which you sort of take for granted. And there is something very confusing about this. Why are you assuming something that you want to prove? Why are you assuming that you know what X is, which you have to add to 5 apples to get 8 apples? Yes? Why am I assuming that there exists this capital F, which satisfies the condition that e to the capital F is equal to z? E to the capital F of z is equal. I'm assuming the answer. And then I'm going ahead and doing something. Okay? This is a very confusing step. And you know, there are places where this confusion is there and you don't realize that there is this confusion. Okay? And therefore you have to be very careful with this. You're assuming the answer and going ahead. And then you must verify that your thing that you get after assuming the answer is actually the answer. Where else have you seen this in mathematics?
So while proving things in contradiction.
No, not just, I mean, in differential equations, have you seen this kind of thing? Okay. You know, in differential equations, you write down some series expansion, you assume there's a series expansion, and then you equate coefficients, and then you say, therefore, the coefficient is this, and therefore, this is the answer. Is that really the answer? Do you understand what I'm trying to do? What I'm trying to say? You see, when you're trying to solve some differential equation, second order, you assume there's a power series solution, and then you call those coefficients an, and you plug it into the equation, and you get some recurrence relation for the ans, and then you say, therefore, the an must be this, and you say, this is the answer. Do you understand that just that much is wrong? Why? Because to come to that power series thing, you're assuming that the power series exists. Yes? What is the next step you do after finding these coefficients? What you must verify is that that power series that you get actually is the solution. Do you know what I'm talking about? Do you understand what I'm talking about? In power series, okay, when you're doing something in power series, so you have second order differential equation, okay, you say that suppose the solution is summation an x to the n. Then you plug it into that Bessel's equation or Lagrange equation or whatever it is, and you say that therefore an must be something. Okay, can you stop at that stage and say therefore the solution is that an which you have found, an x to the n? Does this finish the proof that it is a solution to that differential equation? Can you understand that it does not finish the proof? Because you have come to this stage with the assumption that an x to the n summation is the solution. But that is what you want to prove. So you cannot, say that this is the proof. The next step you have to take is that this is the an that I have found. And then I take this particular an and look at summation an x to the n. And then you have to prove that it satisfies the differential equation. Does this make sense now?
Yes, sir.
Okay, so there's something to be done there. It's the same problem is the same as in primary school when your teacher told you that 5 apples plus x apples is 8 apples. Then what is x? Is x equal to 1? But 5 apples plus 1 apple is 6 apples. It is not 8 apples. 5 apples is 2 apples. It's not 8 apples. 5 apples is 3 apples. X equal to 3. Okay. So your teacher came up with this 3, and then you have to verify that 5 apples, you take 5 apples and you take 3 apples, then you have to verify that you get 8 apples. Now, all of you are going to go and complain to Katre and Verma ji. You're going to complain to Katre ji and Verma ji that Bhate sir is teaching you how to add 3 apples to 5 apples and then tell you that you have 8 apples. But I hope you understand that this is important. Okay, you're assuming something and you get some result. Okay, so you have to show that that thing that you get is actually what you want. Okay, so there's a bit of a fuss that should be made here, which people don't quite see this. What I'm telling you may be hidden inside some very abstruse or a very difficult argument, that you must be sure that if you're assuming what you want to prove when you do something, then you must show that what you get actually does what you want to do, because it is doing it under the assumption that it is a solution. Then you must check that it is a solution. So that's what I'm doing here. Take gz f prime z is, so take gz equal to 1 by z, and then you take this integral, and then you want to show that it is the right thing that it has to do. Okay, so log is not this. And if we define, so if you have defined log on a simply connected domain which does not contain 0 and 1 is there, you're going to define z to the alpha to be z to the alpha is, this is the definition, is e to the alpha log z. So there's time. I'm out of time for